Welcome to the deep dive. We're here to cut through the noise on complex research and pull out the insights that, well, actually matter.
Glad to be here.
Today, we're tackling something that sounds super technical, but honestly, the impact is huge. We're talking innovation, we're talking cost. It's optimizing how we train large language models, LLMs.
Right, and the scale is just
Get
immense.
this. Pre-training, that first big compute-heavy phase, it's over 95% of the cost for some top models like DeepSeek V3.
95%. It's staggering when you think about it.
Absolutely. So even a tiny bit of efficiency, like just a few percent faster, that's not small change. It can literally save millions of dollars.
Millions, yeah.
So our mission today is to really unpack this fascinating Stanford study. Came out September 3rd, 2025. Great title. Fantastic pre-training optimizers and where to find them.
Yeah. Catchy.
Our goal, cut through the marketing, the hype maybe, and figure out which of these new optimizers really speed things up for LLMs and which are, well, maybe just good stories.
Stories based on perhaps incomplete data, as we'll see.
Exactly, because look, for ages, Adam W has been the standard, the
Yeah.
workhorse, right? Everyone uses it.
It's reliable, well understood, it just works.
But here's the puzzle, the thing that's always kind of bothered us. You see all these papers claiming, 1.4x, even 2x speedups over Adam W with new optimizers.
Big claims. Sophia, SOAP, Muon, Mars, the list goes on.
So if they're that much faster, why aren't the big players, the ones spending the big bucks, using them universally? Why stick with Adam W?
That's the core question, isn't it? This gap between the lab results, these exciting papers, and what's actually happening in large-scale, real-world training.
And that's exactly what this Stanford study dug into. They wanted to find the reasons for this gap.
Yeah, it's a really important piece of work for the field. Because Adam W, while good, isn't necessarily the theoretical best. It's just been the practical default.
So these claims of massive speedups, 1.4x, 2x, you can see why people would jump on that.
Oh, absolutely.
Yeah.
If you could cut your training time almost in half or significantly reduce costs, that's a game changer. It changes the economics of AI development.
But then you look around, you see projects like DeepSeek, Yang et al., Gratafiore et al. Mentioned in the study.
And they're mostly sticking with Adam W, or variants close to it. The study does mention one exception, the Kimi K2 team using something like Muon.
Right, one notable exception. But largely, the adoption just hasn't matched the hype.
Precisely. This disconnect, this mystery, that's what the Stanford team set out to solve.
Okay, so we've got the puzzle laid out. Amazing claims, but not much real-world action. So let's get into it. What did the Stanford researchers actually find? What was going wrong with how these new optimizers were being tested before?
They basically zeroed in on two really fundamental flaws in a lot of the previous evaluation methods, flaws that kind of clouded the picture and made fair comparisons difficult.
Okay, flaw number one.
The first big one was unequal hyperparameter tuning. This is really crucial. Many of the older studies, well, they just didn't spend enough effort tuning the baseline Adam W.
So they were comparing a potentially poorly tuned Adam W against a new, maybe better tuned optimizer.
Exactly. Or sometimes they'd keep key settings. Think learning rate, weight decay, these critical knobs, they'd keep them the same across all the optimizers they tested.
But different optimizers might need different settings, right?
Absolutely. And here's the kicker, the really surprising bit from the study. They show that if you just took a standard GPT-3 recipe and only tuned the learning rate for Adam W properly, just that one setting, you could get a 2x speedup for Adam W itself.
Wait, a 2x speedup for Adam W just from tuning it better, not even using a new optimizer?
Correct. 2 times faster. Just by giving the old workhorse the attention it deserved in tuning.
Wow. That single finding almost explains the whole puzzle right there, doesn't it? If Adam W itself could be twice as fast with proper tuning.
It certainly explains a huge part of it. It highlights just how critical fair and thorough tuning is for every optimizer in a comparison. You can't just focus on tuning the new shiny thing.
It's like comparing race cars, but only giving one of them a proper tune-up before the race.
That's a perfect analogy. And it gets worse because optimal settings aren't universal. The study showed, for example, the Lion optimizer needs a weight decay around 0.6, while Adam W prefers something like 0.1.
Completely different value.
Totally different. So if you just pick one value and fix it for both, you're handicapping one or both of them right from the start. It's fundamentally unfair.
Okay, so unfair tuning was the first major issue. What was the second flaw they identified?
The second one was about limited or misleading evaluation setups. A lot of the earlier work was done on smaller models.
Which might not translate to the huge models people train in practice.
Exactly. Performance doesn't always scale linearly. What works on a toy model might behave very differently at, say, a billion parameters or more. Plus, and this is important, many studies judged optimizers based on how they performed midway through training.
Looking at, like, intermediate checkpoints.
Yeah, checking the loss score halfway through the training run.
And why is that misleading? You'd think faster progress early on would be good?
It seems intuitive, but the problem is the rankings between optimizers can actually change or even flip entirely during the course of training, especially when learning rate decay happens.
Ah, so as the learning rate drops near the end.
An optimizer that looked great early on might actually stall or perform worse compared to another one that maybe started slower but finishes stronger. Different optimizers respond differently to that changing learning rate.
Okay, so looking only at the middle doesn't give you the full picture.
Not at all. You might pick the wrong winner. The only way to truly know which optimizer is better for a given task and budget is to evaluate them at the very end of the planned training run. Final performance is what counts.
Right. So given these pretty significant problems in past evaluations, unfair tuning, small scales, looking at the wrong time points, how did the Stanford team build a better benchmark? What made their approach more rigorous?
They were incredibly systematic. First, the scope was comprehensive. They didn't just test one or two new optimizers against Adam W. They looked at 10 different optimizers, and they tested them across 4 different model sizes, from 0.1 billion parameters up to 1.2 billion, so covering a much more realistic range.
Addressing that small-scale issue directly.
Precisely. And they also varied the data-to-model ratio, using settings from 1x up to 8x the chinchilla optimum.
Which is that sort of ideal balance between model size and data amount?
Yeah, roughly. By testing across different ratios, including these overtrained regimes with lots of data, they could see how optimizers behaved under various conditions, which previous studies often missed.
And they standardized the other stuff, like
Yeah.
the model type and data.
Absolutely essential. They used the Llama 2 architecture and Olmo 2-like data mix and Llama 3 tokenization for everything, kept it consistent. So any differences they saw were much more likely due to the optimizer itself, not some other random variation.
Apples to apples, finally.
Pretty much. Then came the tuning, which, as we established, is critical.
How did they handle that, given the pitfalls?
They used a 3-phase hyperparameter tuning process. It wasn't just picking a few values. They employed something called coordinate descent.
Which is like turning one knob at a time, iteratively.
That's the core idea, yeah.
Yeah.
They systematically adjusted each hyperparameter for every single optimizer across the different model sizes and data ratios, letting the process run until it converged on near-optimal settings for each specific combination.
Wow, that sounds intensive.
Oh, it was undoubtedly a huge amount of computational work, but it was necessary to remove that bias of undertuned baselines and ensure a fair comparison for everyone. No shortcuts.
And then, crucially, they focused on the end result.
Exactly. Focus on final performance. Their main yardstick was the final validation loss on the C4EN dataset. That's a good indicator of how well the model learned.
Not just training loss, but validation loss.
Correct. And they didn't stop there. They also tracked performance on a suite of standard downstream benchmarks, things like ARC, BullQ, HeliSwag, to get a broader sense of the model's actual capabilities.
So a really thorough end-to-end evaluation.
Definitely one of the most rigorous comparisons done to date.
Okay, the moment of truth then. After all this careful, systematic work, setting up the fair comparison, doing the rigorous tuning, looking at the final performance, what did they actually find? Did those big 1.4x, 2x speed-up claims hold water?
Well, this is where it gets really interesting, and perhaps a bit sobering for fans of the newer optimizers. The results definitely pour some cold water on those dramatic claims.
Okay, finding number 1.
First, the reality of the speedup is much lower, and it diminishes. Against a properly tuned Adam W., the speedup they observed from any alternative optimizer was never more than 1.4x.
So goodbye 2x claims.
Pretty much, yeah.
Yeah.
At least in these setups. And crucially, that modest 1.4x peak speedup, it decreased significantly as the models got bigger.
The scaling issue again?
Right. For the smaller 0.1 billion parameter models, they saw up to 1.4x speedup from some contenders. But when they scaled up to 1.2 billion parameters, the advantage dropped to maybe 1.1x at best.
1.1x, that's
Yeah.
barely a 10% improvement.
Exactly. A far cry from doubling the speed. It strongly suggests that many of the earlier impressive results were likely artifacts of comparing against a poorly tuned Adam W., and that the true benefit over a well-tuned baseline is much smaller. especially at scale.
That's a massive takeaway for anyone training large models. Don't expect miracles just by switching optimizers unless maybe your current AtomW setup isn't well tuned itself.
Precisely. It resets expectations. Another key finding relates to the type of optimizer. They saw that matrix-based optimizers generally led, at least for smaller models.
Can you quickly remind us what those are again?
Sure. So you have scalar-based ones like AtomW, Lion, Mars. They adjust each parameter sort of individually. The matrix-based ones like Cron, Muon, SOAP, they use the matrix structure of the network, applying more complex updates, like preconditioning with matrices, to adjust groups of parameters together.
Got it. And those matrix ones did better.
For models under 520 million parameters, yes. They consistently gave about a 1.3x speedup over the tuned AtomW. So a noticeable, consistent advantage in that medium-sized range.
But maybe not for the really big ones, given the diminishing returns overall.
The overall trend suggests their advantage shrinks at larger scales, yes. Which leads to the third finding. The best optimizer isn't fixed, it shifts. It depends on the context, specifically the data-to-model ratio.
How so?
Well, take Yuan, for instance. It was consistently the top performer at lower chinchilla ratios, like 1x to 4x. So when data is relatively scarce compared to model size, Muon seemed best.
Okay.
But when they push the data ratio higher, up to 8x or even 16x chinchilla, these overtrained scenarios, other optimizers like SOAP and Cron often pulled ahead of Muon.
Interesting. Why would that happen?
The hypothesis is that in these very long training runs with tons of data, optimizers like SOAP and Cron, which maintain what's called second-order momentum, they consider the curvature of the loss landscape, not just the slope, might be more robust and effective over the long haul compared to Muon's approach.
So the best choice really depends on your specific training setup, how much data you have relative to your model.
Absolutely. No single silver bullet. They also found that among the scalar-based optimizers, techniques for variance reduction used in Nesterov AtomW, Mars, cautious AtomW gave a small but consistent edge over plain AtomW.
So tweaks to AtomW itself can help a bit.
Yes. And Muon actually combines matrix methods with Nesterov momentum, suggesting these ideas can be combined effectively. One last point. The memory-efficient optimizers, like Lion or Atom Mini.
Yeah, what about them? Did they sacrifice speed for memory?
Mostly no. They generally perform very close to AtomW, maybe a tiny bit slower at worst, like 5%, but sometimes even slightly better. So you could save memory without a significant performance hit, which is valuable.
Okay, that's a lot of detailed findings. Let's try to synthesize this. What are the big practical lessons here for people actually training LLMs, or even just reading the next paper that claims a huge speed up?
I think there are some really critical takeaways. Number one, and we've hammered this point, but it bears repeating, hyperparameter tuning is absolutely non-negotiable.
You just can't skip it or do it superficially.
No. A great optimizer tuned poorly will lose to a mediocre one tuned well. Simple as that. You need rigorous, systematic tuning for any fair comparison. The study even showed how tiny changes in hyperparameters could drastically alter the final loss. Rankings can flip just based on slightly suboptimal tuning.
Lesson 2 seems to be about when you evaluate.
Exactly. Evaluate at the finish line. Don't be fooled by early performance or intermediate checkpoints. Rankings can change, gaps can shrink or widen. Judge based on the final performance at your target training budget. That's the only thing that really matters.
Makes sense. And the third lesson?
Context is king. There's no single best optimizer for all situations. The right choice depends on your specific model size, your data-to-model ratio, maybe even other factors. You need to consider your context.
So researchers and engineers need to test and choose based on their specific scenario, not just grab the optimizer that won in some generic benchmark.
Precisely. And finally, the study also highlighted some interesting common behaviors across optimizers, things we thought might be specific to AtomW seem more universal.
Like what?
Like parameter norms tending to track the learning rate schedule, or gradient norms sometimes increasing during learning rate decay without actually hurting performance. And critically, different optimizers, despite their internal math, often showed quite similar generalization behavior. Their training and validation loss curves tended to follow similar patterns relative to each other.
So under the hood, they might be doing different calculations, but the overall learning dynamics and generalization often look surprisingly alike once properly tuned.
To a large extent, yes. Which again emphasizes that the optimizer choice, while not irrelevant, might be less about fundamentally different learning paths and more about achieving efficiency within a broadly similar learning process.
This has been incredibly insightful. It feels like we've really peeled back the layers on this optimizer puzzle. The core message seems clear. those dramatic speed-up claims, largely inflated by unfair comparisons.
Yeah, the reality is more modest gains over a well-tuned Atom W, and those gains shrink as models get bigger.
So the real keys are rigorous tuning for whatever you use and evaluating properly at the end of training. For you listening, the takeaway is definitely be skeptical of big optimizer claims unless you see evidence of that methodological rigor.
Couldn't agree more. Due diligence is crucial.
Okay, let's wrap up with a provocative thought. This study went up to 1.2 billion parameters, right? And saw the speed up shrink from maybe 1.4x down to just 1.1x.
That's the trend they observed, yes.
So if that trend continues, as we build truly massive frontier models, 7 billion parameters, 70 billion, even bigger, could it be that Atom W, the old reliable, actually remains the best choice? Or maybe even becomes better relative to alternatives at that extreme scale?
It's a fascinating question. The study's own scaling projections hinted that muon might actually perform worse than Atom W at 7B parameters in some settings.
Right. So are we hitting a wall where current optimizer improvements just don't scale up? Will we need fundamentally new ideas, completely different approaches to optimization to get the next big leap in training efficiency for these monster models? Or is Atom W, maybe with minor tweaks, already close to the practical limit for now?
That's the multi-million-dollar question, isn't it? Whether the future lies in refining Atom W, finding truly stable new optimizers, or perhaps shifting focus to other areas entirely for efficiency gains.
Something for all of us to definitely think about as we watch this space evolve. Thanks for that deep dive.
My pleasure. Always interesting to unpack these studies.